So a few months ago, I met some people that were willing to join forces on arts parts testing. One had multiple pieces and wanted to collaborate, and another had lab access and the expertise for exactly the tests we needed to do. This is a dream come true. A week later, I connected with someone else who's done some serious implant sample analysis and who also happens to own some UFO fragments that he personally recovered in 2011. So with all of this in place, I got the arts parts and the San Augustin samples tested at a top tier lab. I drove thousands of miles because flying wasn't an option. Arts parts is already linked to 2 air crashes, one of those being the Mantell incident. So yeah, no flying for me. I spent hours and hours, days in the lab, working shoulder to shoulder with these scientists. We were gathering the best SEM and atomic level TEM pictures and data that on samples that I've seen to date. The sample owners, though, were not present for this for multiple reasons. Then came the trip home. My life was seriously threatened on the drive home. I'm not going to go into a lot of detail on it here, but if you want to know more, I posted a story about it on Reddit. Nutshell is that there was a 15-minute-ish long car chase through desolate, mountainous, icy roads. And just a few minutes after that was over, there was some hovering lights above my car in the middle of absolutely nowhere. It was as sketch as can get. So that said, this work is not for the faint of heart. So once I got home, I started going through all of this data that we had collected. For months now, I have been just day and night, every single day, I've been going through and pouring through this data and going through white papers, trying to see what could possibly relate to this. So a few weeks ago, as I was getting the APEC presentation here all prepped, I gave the arts parts owner a heads up, not our arts parts, but the other new samples that we tested. And then I beta tested a couple of these slides on Reddit, and it blew up really fast, like hundreds of thousands of views in a few days. And then came the miscommunication, the phone call. The sample owner requested that I pull everything down and that I don't use any of their images of their samples. Because, in their view, peer review is the only valid way to present this. Arrow and Oak Ridge botched their report. The full Oak Ridge report isn't even up for real peer review because we only have a whitewashed version that's a fraction of the original size. And for anybody who's been following my work, you know that open sourcing is very near and dear and at the core of what I believe, but it's kind of naive. It's how I've gotten this far. Some of that data, I already leaked it out there, so it's already out there. I already, though, deleted those posts. Like, while I was on the phone, I was deleting the posts. I don't want to do wrong by anybody. And I had to remove 100 images of their samples from this presentation. I had to gut this presentation completely. Still got some pictures of the Falcon space sample, but we need to give the peer review the chance that it deserves and allow these scientists that are putting in the work to get the credit that they're due. And that's peer review is pretty much the only possible way that we're going to be able to legitimize this sample to the degree necessary to be able to take on Oak Ridge's report. So I'm not going to share any samples or any images of any samples that I don't own. But I still am going to share my observations, you know, what I see, what I think I see. I'm an amateur, so take what I say with a grain of salt on this, because material science is not my expertise, though I am learning very rapidly that it is a very complex field. Yeah, Yeah, so I'm going to break down my analysis. I'm going to reference the key papers. I'm going to highlight some of the overlaps between other samples and our sample, just highlighting what's in our sample that I feel much more confident now would be in multiple samples. Yeah, the level of technology that's present in this material is unquestionably advanced and pretty daggum sure did not exist in 1996 or earlier, as the Dalnegorsk may indicate. That said, let's go. So let me get this slideshow going. All right, just to recap for everybody, I'm gonna bring up to speed real quick on what the arts parts history is here. So as the story goes, 1947, we get a crash. Some people call this the Roswell sample, but there was actually multiple crashes in the July 1947 timeframe within days of each other. This one was the White Sands crash. The original owner, we're going to call him grandfather, he's on the scene doing the crash recovery process. While he's there, he manages to sneak off a couple of pieces of the underside of this craft. He doesn't say a word. He keeps this all under wraps, keeps it in a shoebox, and then on his deathbed in 1974, he gives custody of this shoebox to his grandson. And then this grandson, after having owned these things and tried to do stuff and failed at getting any answers with it for a long time, he ends up giving them over to Art Bell and Linda Moulton Howe in 1996. Over the course of a few months, he sends 5 letters, and with some of those letters, he sent some packages, and in those packages, there was multiple samples. Then fast forward from there, lots of testing was done in between then and now. In 2024 of April, one of those bigger piece samples eventually made its way over to Oak Ridge National Lab, and they published a classified report. And then fast forward to June, our team gets our own little tiny piece from one of the scientists that had held on to it during that last, since 1996, that it had been going to a lot of different scientists, and one of them kept a little piece and held on to it, and eventually it made its way into our hands. So now we have a sample. 2 days after I gave my July presentation, which was about a week after we got the sample tested, that's when Oak Ridge released a 10-page report saying, this is a nothing burger. Nothing to see here, guys. Okay. Then, this year, we have 3 more arts parts samples that are tested. Hopefully, we will see some answers coming out of that in the very near future. I say very near. I don't know when they're going to publish their stuff, but I'm hoping that it's going to be sooner rather than later. So here's an overview of what I'm going to give you in this presentation. We have 3 additional arts part samples were tested. This is a really big deal, even though I can't share much about it. I'm going to go over the scanning electron microscope, the electron dispersive spectroscopy, and the transmission electron microscopy. You see a lot of cool stuff when you look at these little things really close up. There was some weirdnesses in the scanning microscope that confirmed some things with what I've seen in our sample. There was probably the most important thing. The slide, there was 1 out of those 100 that I got rid of that breaks my heart to get rid of, because in my mind, it's at least a steam and barrel, if not a smoking gun of advanced technology. Nanometer-sized things that are indicative of high engineering and high technology, which was really interesting because back in November, I got a chance to talk to Eric Davis while he was presenting at Seoul, and he brought up this thing called programmable quantum matter. I'm going to get into it. He also talks about quantum dots and in his DIRD, which is pretty interesting. I'm going to go over some of those as well. I'm also going to talk more about the whiskers that we've seen on our sample. I'm going to go over the similar craft, talk about Ubatuba and how maybe that relates, talk about the 1986 Russian Roswell event called Dalnegorsk. I'm going to go into the Quincy St. Clair, not the previous speaker, but Quincy St. Clair patent that seems like it may have some overlaps. I'm going to talk about the nanowire that's on our sample and all the possible things that it might be doing. Then I'm going to go into the engineering stuff. Can we actually maybe reproduce this ourselves? As well as the fact that we got ourselves a terahertz laser, which is pretty awesome. And then I'll end it with a good transition into the isotopic stuff that the next presenter, Dr. Sadagis, is going to go into. And I'll wrap it all up for you with a summary. All right. So I do apologize. I've had 2 days to put together this presentation. I have not slept much, so it is going to be a little bit rough. I'm just going to apologize in advance. So scanning electron microscope, you're looking at stuff really close up. In that we see, well, in that I saw some thickness measurements of magnesium layers that I now feel more confident on what the thicknesses of these layers are. I would say it's about 150 micron average layer for the magnesium zinc layers. Also, important takeaway is there's these rings of the microspheres that rupture. And they seem to have, not all over the place, but in enough spots to make me think there might be a pattern there. They seem to be arranged in rings. And the diameter of those rings may correspond to some far infrared low terahertz frequencies. Here's a zoomed in picture of Falcon Space's ARTS part sample, where you can see some of these microspheres. You can see how there's kind of a ring there in the center that's attaching them all. That's not normally there with most of these things. That's just helpful for this picture to be able to show you the arrangement that these things are forming in. In another scanning electron image that we have for the Falcon Space sample, here you can see these things have ruptured all over the place. Like most all of them have ruptured at a fairly significantly large size, anywhere from 20 to 40 microns. That's a really important piece of information there, that you're seeing the smaller ones have not ruptured, but the larger ones have ruptured. That indicates a process is taking place. Also in this image, though it is somewhat difficult to see, there is a ring pattern of the ruptured spheres. On the left side of this image, you can see our EDS, where you can see the composition of these things. And this is, I've zoomed way in and it's super blurry, I know. That is one of the ruptured spheres that hasn't ruptured as much as the ones that you see on the right. It is in the process of rupturing, which once again, processes are important for understanding how something might work. In that image, you can see the turquoise is zinc, the yellow is lead, and then the green that's not set at the bottom, the green is oxygen. So we can see in the smaller unruptured ones in that left image that they are mostly composed of zinc. And sometimes that zinc gets oxidized, and it does seem like there is some lead present around it. And you can also kind of tell that these things are hollow inside, or if they did have something inside, it is all gone. Here is some similarities to some other zinc magnesium alloys. In this instance, we can see some nanoparticles of zinc. And you can see how they arrange themselves in a circular pattern like that. This is just somebody else's paper from some other experiment they were doing. This is just an interesting other picture of what a zinc microsphere kind of looks like. And if you look at the scale on that, it's kind of hard to read. It's a little blurry, but it says 20 microns in the lower left side of those images, which is somewhat in the ballpark of what we're seeing in ours. So that's interesting. This slide, once again, it's a little bit rough. I'm not going to go into the exciton polaritons, mostly just the plasmons. You may need to understand and get just a little bit of background on what a plasmon is, because it seems like some of these things might have plasmonic capabilities. So a plasmon, nutshell version, it's just an oscillation of the electrons that are the conductor electrons in a metal. Most of the time, the frequency ranges are in the UV, but sometimes it actually does come down into the terahertz in specific applications. That's about all I'm going to go into on that one. All right, so in the center image here, you can see a 20 nanometer scale. So we're looking at much, much smaller than 20 microns, 1,000 times smaller than 20 microns, right? This is like a transmission electron microscope TEM image here. And you can see the sizes of those dark things is somewhere in the ballpark of 10 nanometers, give or take. That is not a picture of Art's parts. But if one were to look down at the small scale, one might see grains that are small like that. And also arranged in ring shapes. Well, this is interesting because when you arrange zinc grains at just the right spacing apart from each other, they actually can create a waveguide of plasmons, of these waves of electrons. That's very interesting. It may not actually be going on in the sample, but the sizes and the spacings of these things suggest to me that it's worth further inquiry. On the right side, you can see I have a picture of the Oak Ridge National Lab report picture for whatever that's worth. And that is a much, much zoomed out picture. It is 200 microns compared to the 20 nanometers of the center image. But in that Oak Ridge image, you can see all of the bright pink spots. That's all the zinc. And since we know that it's 150 micron average thickness of magnesium, you can see that this is actually a lot of layers stacked atop each other. This is not just like one single layer. And you can see that it appears as though the distribution of the zinc in the Art's parts is, it alternates. It's like, it's there for 2 layers, it's not there for 2 layers. So that's interesting. Probably a process taking place. So I said a little bit of stuff about terahertz. I'm going to have to give you guys a little bit background. Most people may not be familiar with what terahertz are. So you can approach terahertz from the bottom up or the top down frequency wise. You can approach it from the RF side and you can get into like the hundreds of gigahertz, not quite the terahertz, or you can approach it from the optical side with light and you can try to bring it down, down, down and try to get down there. But there's this range of 1 to 10 terahertz that's really, really hard to get to. And that's unfortunate because there is an absolute megaton of magic that happens in that band. So 1 terahertz is about 1 picosecond or 1,000 femtoseconds. 10 terahertz would be a tenth of that, 100 femtoseconds. In this magical range that we're going to keep an eye on of 3.2 to 5.6, that would be somewhere in the ballpark of 180 to 300 femtoseconds. The wavelength of this, we're looking ballpark 30 to 300 microns in free space. When you actually go in materials, it can change that number a lot. But so in the magic range, we're looking at somewhere between 56 to 94 microns. Black body radiation, this one's kind of interesting. So this is heat. Black body radiation is heat, right? You're constantly emitting black body radiation from your body, and that's why you can get picked up by a thermal camera. Well, that thermal camera is picking up some of these frequencies. It's just a much, much higher terahertz that it's picking up. So down in the 150 to 270 Kelvin range is where we're looking at for that magic window of terahertz we want. And it turns out you can convert, sorry, I meant to say you can convert terahertz to temperature, right? Because like I said, it's heat. And that would also correspond to anywhere in the ballpark from -4 Celsius to -120 Celsius, thereabouts. Room temperature, you're somewhere around 300 Kelvin, which would be 6.2 terahertz. In a little bit, I'm going to go into the whole temperatures that it looks like is pretty regularly observed on UFOs, which happens to be right smack dab in between that 3.2 to 5.6 terahertz. At -50 degrees Celsius, we're looking at halfway between -4 to -119. All right. This one's going to be just a little bit out there. I was debating even leaving the slide in, but so some folks have talked about terahertz in completely different applications. Travis Taylor was talking about cow blood. There's this stuff in cow blood called albumin. Well, there was a study done back in 2009 that was noticing that some weird stuff happens in cow blood at, once again, in this magic window range frequency. And yeah, weird stuff happens to cow blood, according to Travis Taylor, and there might be a relationship there to UFOs. Additionally, terahertz in the biology realm, it's its whole niche. So microtubules, the cytoskeletal structure that holds your brain cells, your neurons together, also what Penrose says is where your consciousness is. It turns out you can really mess those up with terahertz, so keep your skull away from any terahertz sources. Additionally, DNA, the little hydrogens on your DNA start wiggling at this stuff. And so terahertz can actually unzip your unzip your RNA. Yeah, so there's some interesting relationships in nature to specific magic window of terahertz. That's all I wanted to say with that. So the temperature study that I was talking about, I was saying it was about minus 50 degrees Celsius. Well, first study that I came across was the 2013 Agadia UAP. SCU did a study on that. They saw, in their study, they said that the whole surface of that craft looks like it was about 105 degrees Fahrenheit. That's a lot hotter than negative 50. But the ambient air was only 80 degrees Fahrenheit. So whatever that thing was, it was warm. But according to this study that was just put out at the end of January, that is probably one of the largest UFO studies, at least the largest laundry list of authors on a UFO study that I've seen to date. In fact, the following presenter is one of the authors of that study. But in that study, that's where they're saying that it seems as though very, very cold temperatures are actually associated to UFOs. This is a very important deal that we have whole surface temperatures, because it's gonna guide a lot further research into this stuff. Also, it does tell us some other stuff here, that in the cases where people have gotten like sunburns from UFOs, that is indicative that maybe some weird stuff is going on regarding any warping aspects. Maybe. All right, this part was pretty exciting. So story goes, I go to Seoul and I get the chance to ask Eric Davis a question while he's on stage. I'm so happy, right? This guy worked with Puthoff for years and years and years, and Puthoff was the main go-to guy for testing arts parts for Linda. So the chance to get to ask him about materials testing, very rare opportunity. Whatever he can, say without getting in trouble. So I just asked him, what can you tell me about materials tests that you've seen that are interesting? Here's what he said. He said, we haven't been able to figure out their technology. The physics, engineering, the manufacturing technology just doesn't exist at this time. This is a couple of months ago, by the way. He says, we're just barely scratching quantum materials now and how to create, this is the money, programmable quantum materials. He goes on, but that was something that came out of this whole thing with respect to some of these aerospace companies that he was interfacing with. Aerospace companies. That is, they made some very interesting discoveries in the advanced material science aspect of the hardware that was recovered. If you look at that lower right image there, you will see one of the first pictures that comes up if you do a Google search on programmable quantum materials. That picture is of some really fancy stuff where you're basically etching into graphene, and you can etch shapes into it, and those shapes are going to confine little packets of electrons and make them do some funny stuff when they're confined. I include that slide because I can't include a different slide. So Eric Davis, he wrote a DIRD, a defense intelligence document, back in 2009, 16 years ago. In that document, he's got, once again, some relatable to arts parts things in it. He's talking about nanowires with programmable matter, programmable material. He's also talking about quantum dots, which is also a very interesting thing with regards to arts parts. He says that quantum dots can actually do a whole host of magic things. They're not just little light capturers. They can actually do a whole lot of magic. One piece of magic. Oh, I said they're at the bottom. They can change the optical, electrical, thermal, or magnetic properties depending on how you tweak them. That's a lot of functionality for a little nano bead. One of the more interesting things I found out about quantum dots is you can use them to make coherent terahertz. That sounds useful. In fact, you can make a quantum dot that can just absorb the natural background heat, black body radiation heat, and it can emit coherent terahertz on demand. That's amazing. This is a thing. No, that's a 4-year-old paper. No idea that this is a thing. You can take heat and convert it into coherent laser, just ambient heat, using nothing other than a nano-sized bead. Wow. You can also take one of these quantum dots, and one way you can tweak them is you can coat them in other things. Well, one of those things you can coat them in is zinc. Not going to go into a whole lot more on that. Lastly, that thermal side of things, you can use quantum dots to convert, instead of heat to terahertz lasers, heat to electricity. That would be very, very useful. If you had a heat sink that could actually convert the heat from your computer processor into usable electricity, imagine how efficient a computer you could have would be. That's a very valuable piece of tech right there, and it's been out for 7 years now. Well, at least I think this is a hypothetical paper. I don't think they actually did the experiment in it yet, but they did reference associated experiments where they're starting to show that it's possible. More on quantum dots. Turns out that you can have lead quantum dots. This paper doesn't say it, but I would imagine you might be able to coat a lead quantum dot in zinc, I'd imagine. Don't know why you'd want to do that. Here's some pictures, close-up TEM pictures of what a quantum dot might look like. On the left there, that one's just a red quantum dot that's made of, I think it's cadmium, selenium, or zinc, cadmium, sulfur. You can see the size, 10 nanometers. You can see how you got aligned grains there, and then it's got like a fuzzy like border on the outside. It kind of looks like a cell. On the right there, once again, you can also see another image of what quantum dots made of zinc might look like. Moving on to some of the whiskers that we have observed in our samples. So these arts parts pictures you can see here, there's no scale on this, unfortunately, because we were looking at this under our metallurgical microscope. We didn't have the software set up at the time to be able to have scale on there, but I can tell you that the diameter, the thickness of one of these things is in the ballpark of about 1 micron, to give you an idea. Whiskers can do some stuff, it turns out. They're not useless. First off, they may be indicative that this thing has been exposed to a prolonged electric gradient. That's important. Once again, that's a thing that tells us maybe a piece of the process puzzle. But additionally, when you start zooming in on terahertz stuff, whiskers have actually been known to have some interesting properties with relation to terahertz. Now, I'm not saying that's what's going on in arts part samples. I'm just saying that this is a potentially relevant paper I came across, somewhat related, where they were showing that in bismuth whiskers, that it can cause a polarization. It can rotate a terahertz beam, and that it has a higher refractive index than like bulk bismuth, which makes sense. I mean, you would think it would. So if you look at the upper right or upper left image, you can see the scale of these things is a bit larger than the scale that I was saying, right? The diameter of those things looks orders of magnitude larger than ours, but can't help but notice how that upper left image looks like this forest of crisscrossed whiskers like that. That's a very interesting image to me. I can't help but look at our bismuth ones, but the jury is still out whether or not these things are made of bismuth or they're made of zinc, or maybe there's both. Maybe you're not limited to just one kind of whisker. All right, lower left image there, that is a picture once again from the Oak Ridge National Lab report, if you can trust it. It's kind of hard to see because I made it too small, but I did a little bit of back of the napkin, like pixel counting calculations there. You can see that all those black dots there, that's the bismuth, right? And you can see that it's not a solid crystal. If it was a solid crystal, the idea that it might be acting as a waveguide would make a lot more sense. But it seems as though this thing is maybe not a waveguide because it's so discontinuous like that. So the sizes of those black dots, those bismuth dots, is somewhere in the ballpark of 100 nanometers to maybe 1,000 nanometers, a micron. And the total thickness there in the middle longer green line, that says 800 nanometers at that point. So saying that the bismuth layer is 1 to 5 microns is not accurate. In some places, it is much, much, much thinner and discontinuous, which turns out that there might actually be a use case for these things if they were discontinuous. On the right side, the lower right side image, this is a paper talking about bismuth nanoparticles, some of them in the sizes of what we're seeing in that Oak Ridge image. In that lower right image, the lower left of that, under the energy loss column, you can see we have 200 nanometer and 500 nanometer spikes there in the EELS. EELS is just another measurement tool you do during TEM to see a couple of other interesting features of a thing, usually like a little elemental analysis, but you can also do some plasmonic stuff with it. It's a useful tool. So it's interesting what I observed there, knowing very little, I will admit, very little about EELS. But I can't help but observe how you have a fairly well-defined hump there in the 200 and 500 nanometer that you don't have in many other places. It spreads out at some of those other sizes. So that's interesting. I wonder if that plasmon relationship there might be important. Let's keep going. So a thin film bismuth, if this thing was a thin film, which it's not, but just to give you an idea on maybe some of the other effects that happened with bismuth, is when you hit bismuth with a circular polarized terahertz beam, there's a process that takes place within the bismuth that generates a current inside the bismuth. It's called circularly, I can't remember. I'm sorry. I'm pretty tired. It's photocurrent. Basically, you can use light to generate a current in the bismuth. And that current can then generate its own emission on the other side of the thing. That emission, what goes in must come out. You can get terahertz out of bismuth. For that, that's 30 nanometers, which is a little bit smaller than what we just saw in the those nanoparticles. But I want to say in that paper, maybe it tops out at like 70 nanometers is where you start getting saturation. So interesting, though. There's definitely a terahertz relationship with bismuth at small scales. Then I found this paper. This one's talking about how somebody took bismuth and they put gold wires on it, which I'm going to get to in a little bit here on why gold wires on bismuth might be important. But just the fact that somebody did a test like that is really interesting. Unfortunately, their testing was all in the telecom frequencies, which is hundreds of terahertz, extremely short wavelength. They're like 1 micron wavelength. We're talking, right, 50 to 90 micron wavelength terahertz. So definitely not 1-to-1. And the radius of the gold nanowires they were using was 17 nanometer gold wires, which, once again, it's not in the micron range gold nanowires that we're talking about with the arts parts. But what happens when you take gold wires and embed them into bismuth is that terahertz beam that comes out, yeah, you can actually cause that thing to rotate. You've now put a polarizer, a circular polarizer on that thing in the form of these gold wires. And it actually, it's messing with this very obscure type thing, but it's called Faraday rotation. Faraday rotation is interesting from Ray Stanford's stuff. He has that really famous picture of those Faraday rings on the edge of the craft, which are indicative of extraordinarily strong magnetic fields. In order to twist light that many times around, in order to get that many rings, you have to have an insanely strong magnetic field. Well, bismuth does funny magnetic stuff, and you put gold wires on it and you hit it with terahertz, and it does funny magnetic stuff more. Nowhere near the degree of like the 12 plus rings that we're seeing on his stuff. That's like, you know, kilotesla or gigatesla level like strengths. But maybe there's some kind of relationship here between the Faraday rotation of gold wire embedded in bismuth, Faraday rotation observed in UFOs. So this is going a little bit deeper into what's going on in bismuth. So you can hit bismuth with a right hand circularly polarized beam or with a left hand circularly polarized beam. And different things happen. So if you were trying to get a specific effect out of bismuth that only works with one circular polarization direction than the other, it's probably another avenue to look down. All right, let's get into some of the similarities I'm noticing in other craft that might have some overlaps with arts parts. First one, Ubatuba. So Ubatuba, if you're not already familiar with it, a fisherman is out fishing down in Brazil, Ubatuba, Brazil. And there was a UFO flies over his head, drops some molten metal, and years and years and years later, eventually makes its way by the late, I think it was in the 30s or something, it supposedly happened to the guy. And then by the 50s, this thing actually gets tested. So it's been tested many, many times since then. And there are some very strange things about it, which may support that it is indeed anomalous. One of the things that relates to arts parts, though, that I'm noticing is we got magnesium. It's much, much higher magnesium than what's in arts parts. Arts parts is like 97% magnesium. This is 99.8% magnesium. That's so much more magnesium. And the zinc is much, much lower. We're at like 2.5% zinc in arts parts. This thing's all the way down at the, I'm not going to say percent, this is parts per million. But there's zinc in there. One other thing I want to mention about this is maybe this could be indicative of what is going on with the craft. This stuff came down in metal molten globs as if it was useless to the craft, as if it was throwaway garbage. And it happens to have much, much less zinc than what's in arts parts. Does that mean that those little zinc microspheres might be getting all used up? And maybe zinc is consumed in the process of whatever this stuff is supposed to do? Maybe. I don't know. I'm just making an observation. All right, this is the one that gets me excited. Dalnegorsk. When I came across it, I haven't been able to stop thinking about the Dalnegorsk case since I came across it. This is so cool. So in 1986, January, there was this tiny, tiny little mining town in Russia that is in the mountains. The height 111 thing there, that's because it was like a mountain that was 611 meters above sea level or something like that. Like it's a super prosaic name. But it's 38 and a half years after the original Roswell Arts Parts event. And it's 10 years before Arts Parts enters the public scene. So this, at a bare minimum, even to a skeptic, this can predate, if indeed it has enough overlaps, it can predate Arts Parts back from 1996 back to maybe 1986 if we consider that this could come from a similar craft. I have got this meta study going on all of the elements present that were tested in this stuff back in the 80s. And I've compared all of those against all of the elements that we are observing in Arts Parts. What you see before you, that is just the elements that are the same. There's some differences in the elements in there as well. Might be indicative of transmutation. I'm not going to hang my hat on that, but it might be. Don't know. But it's got sodium, silicon, iron, nickel, zinc, molybdenum, gold, lead, bismuth. That's a lot of overlap there, just if you're looking at like nothing other than the elements that are present in these samples. But it turns out there's also some physical characteristics that are the same too. It has gold nanowires, and it's got those little ruptured zinc lead microspheres that I was talking about. This thing has hollow lead microspheres. So here's the book. By the way, if anybody goes back and watches this after I've uploaded this presentation, I got links all over the place throughout this whole presentation. This is a book I found that was all in German. I translated it. There's a link in the presentation for this book. But you can see in those images, they're showing the little gold nanowires. And actually what they're saying is that these things are 17 micron diameter, and that they are made of quartz with a gold core. That is extremely unique and very relevant to Arts Parts. In the lower image there, you can see there's another picture of their quartz-clad gold wire sitting on the surface of the sample, like it's part of the sample. And here's a side-by-side of that image and our Arts Parts quartz-clad gold nanowire. It's not a one-to-one, but it's got some similarities. Also, let's take a step back for a second. Remember that DIRD, the Defense Intelligence Document that Eric Davis wrote? Well, in that document, one of the things he talks about is these quantum dot particles being on the outside of a control wire. I'm just making an observation here. If you look at these quartz-colored wires on here, do you see some bumps on there? Do you see any similarities between that quantum dot particles control wire picture and our sample? Maybe. Here is some other parts of the Dalnegorsk recovered materials. The important part here is in the center. I got a picture there for you of our EDS ruptured zinc lead microsphere. And below that is the picture of the lead droplets that are like hollow in the middle. Now, I think there is a size difference here, also an elemental difference. You know, if they're saying those are lead and we only see like a bit of lead in ours, and how hollow do those look? I mean, you can go after that all you want. Like it is far cry from a definite overlap. But maybe a relationship, if anything, maybe this can once again help give us an idea on some processes that are taking place, if indeed these come from similar craft. Additionally, though, they also talk about a gold mesh. Now that could be very, very useful, extremely useful. In terahertz applications, gold mesh, that's a thing. So here's a little blurb from that book where they're talking about the gold nanowire that's clad in quartz. The scientist said that the metal fabrics that they found, which I believe is the gold mesh, says that a natural or a terrestrial technical, meaning human made on Earth, origin is excluded. That scientist, for the life of him, could not imagine any way in 1986 that somebody could be making a gold nanowire encased in quartz at the sizes that they're seeing, nor these gold meshes at the sizes that they're seeing. Like, it wasn't a thing at the time. 10 years before Arts Parts. So here's an interesting thing. So Quincy St. Clair, related to the gold nanowires. Quincy St. Clair, if you know, you know. So this guy has a lot of really interesting patents. Some of them are way out there. Some of them are less so. This one, I'll put it somewhere in the middle. So in this one, he is talking in 2004 about a braided gold coaxial cable. In his case, he's saying a gold within gold, but you could replace the outer gold with quartz and it would perform better. But in this patent, he's talking about a gold coaxial cable in the micron size. He's saying that it couples to space-time itself somehow. It's a dimensional manipulator somehow. The important part is that he says it just so happens that according to all these calculations he's got, should be about 16 to 17 micron diameter. That's interesting. I wonder if he knew about the Dalnegorsk thing. Maybe he knew more. Maybe not. Maybe it was just dumb luck, but that's what's in his patent. Well, he's talking about tapping into subspace or dimensional energy or something. It's worth noting that in the first Arts Parts letter, the grandson is talking about what happened after the crash. So according to grandfather, the crash happened and there was a survivor that grandfather ended up talking with a lot for like 6 months. That ET said that in the process of the crash, he goes through the whole story on what's like started with the crash and then what went on during the falling and then, you know, once they actually landed. But what the alien said was that they had two modes of propulsion on the craft. One is the dimensional power plant, which sounds more like a generator, but he's saying that they use it for deep space travel. Okay, that might be related in some way to what Quincy St. Clair is talking about with the dimensional subspace something or other with gold nanowire. I'm not sure. Good takeaway from that, though, is that there is two different forms of propulsion according to a document that cannot be like verified, right? We know that this document went to Art Bell, Linda Moulton Howe, but we don't know if the grandson is telling the truth or not because we haven't identified grandson. All right, here's some calculations. I put in definite quotes because ChatGPT, bro. Okay, I was doing this in 2 days. I didn't have time for it. So I'm going to say order of magnitude. I'm not going to hang my hat on this, but I'm going to say order of magnitude. If it just so happens that you had a quartz-clad gold nanowire of the dimensions that Quincy St. Clair is talking about, you're looking in the far infrared range. You're looking at the low terahertz range. I feel confident enough to say you're in the single-digit terahertz, but I'm not going to hang my hat on it. All right, so we're seeing some similarities here and there. We're seeing quartz case nanowire might be in that low terahertz range. The bismuth layer, it just so happens that there may be some interesting plasmonic effects at these particular sizes. I didn't get into it, I apologize, but at some of these similar frequencies as well. The diameters of these ruptured microspheres happens to also be in the ballpark range of this far infrared low terahertz, which might be also indicative of the specific frequencies that we need to zoom in on. Maybe we can take that 3 to 5 terahertz and we can narrow it down to 4 or something, right? Maybe if there were zinc-sized nanograins present in this thing, they might be interacting as far infrared low terahertz plasmonic devices. And then, of course, the magic from Lou Elizondo's book, Imminent, he just puts it right out there. He says, this was the frequency that was really interesting. Gives a range 3.2 to 5.6. Here's some more stuff about how you can improve a nanowire by cladding it in quartz, because you get this negative refractive index of the quartz, and it's a whole thing. It improves your nanowires. Also, though, if you take a nanowire, if you take a bunch of nanowires and you position them in the right way, in the right shape, you can end up steering, doing beam steering. That might be useful for something. If you have a whole array of them like that, you could end up twisting a beam. Once again, we come back to circular polarization and twisting beams. I can't help but notice that that gold nanowire that we got on ours happens to have an angle in it. So got a protractor out, measured the angle. Image on the right there is the scanning electron microscope image of our sample. So the thing is that on the bottom arm that you see here, you can see how it kind of kicks up. It's got a little bend up there. So I measure distances and angles to both. It looks like at the elbow there, the long elbow, it looks like that's at around 120 degrees. And it looks like that little kick up at the end, it looks like that's about a 25-degree kick up. So overall, from tip to tip, you're in the 100-degree range, give or take. I also, using the scanning electron microscope image you just saw, I overlaid that over the other one. And then I took the scale from the scanning electron microscope image to try to come up with a ballpark length on these arms of this thing. There's better ways of doing this, way better ways that look way less messy than this. But this is what you get with a very rushed presentation. It turns out that this potentially phase shifting something or other metasurface gold, if it is maybe gold nanowire, the length of one arm is around 260 microns. The length of the other arm in total is around 240. That little 20-degree or 25-degree bend that we see there, the length to that point from the elbow is around 130 microns. It's right around the halfway mark. Well, that's really interesting because the average layer thickness of the magnesium and zinc is 150 microns. I might just be noticing things that aren't there. Maybe there's no relationship between the lengths of these arms and the thicknesses of the magnesium layers. But it's in the ballpark. The overall length of those is quite different at 60%. But that bend there, that little 20-degree bend there, if we look at that length, if that's important, that's within spitting distance of the average thickness of these layers. From Lou's book, we can see that Lockheed tried to make their own, and he included a picture in there. And I don't know if that picture is the actual one. Supposedly, they failed. The unnamed aerospace company, they tried to make it, and they claimed that they failed. I found a similar image of an engine vibration test block, which is something that maybe an aerospace company would have, that looks in the ballpark similar. I don't know for sure if the image that Lou has there is correct or not. I don't expect any wrongdoing on his part, but I don't know if that is indeed supposed to be a layered metamaterial. But if we wanted to make this ourselves, this is where the rubber meets the road. We're engineers. We don't really care about theory. Just let's make it and make it do the thing. Can we buy the parts? Can we shove them together? Can we make this happen? I'm going to put a low maybe on it. Not a hard no, but closer to no than yes. And the reason why is because some of the nanoscopic sized things in this are not something we're going to be making anytime soon. But we could buy bismuth nano powder, make little nano things. We could buy gold mesh grid of the sizes that they describe. And then we could coat that in quartz. We could purchase some terahertz sources. There's a lot of stuff we could do if we wanted to try to make this ourselves on the cheap, right? That's the other thing, is doing this on a budget, and not in a, super top-notch lab, but, garage labs like we got. Well, we did happen to find a terahertz laser. I mean, that's pretty awesome. So this terahertz laser, the previous owner, I believe, may have been Sandia. I don't know for sure, but I believe it might have been, based upon its previous location. This terahertz laser, when operational, goes from 250 gigahertz up to 7.5 terahertz. Hey, would you look at that? Falls right within our magic window frequency. That's pretty awesome. Now, because we got this for a steal, it hasn't been serviced in about 15 years. So we are in the process. This is late breaking news. We just got this thing, and we just got the service manual for this thing like a couple days ago. So it is a work in progress before we're going to have this thing up and running. But we're a lot farther than not having anything. So here's some more pictures of this thing. Lasers with Z, because lasers are awesome. This is one of those don't mess with it lasers. It's a really, really, really dangerous laser. So we have to make sure that we dot our I's and cross our T's to the nth degree before we even turn this thing on. But we're working on it. All right, and then I'm going to transition it here. The elemental analysis, I do want to make just a little blurb here on the isotopic analysis. So this stuff does some really cool things with regards to radiation. Like, it just gobbles up the neutrons in a way that is really unusual. It doesn't do it all the time. It only does it at like the highest possible energy. And it saturates really fast too. So it gobbles them up, and now it's done gobbling them up. Like, it's really, really weird. So we did that little lower right-hand image you see there. That's a little puck of uber, super duper radioactive stuff, some of the most radioactive stuff known to man. And our sample is sitting on it there. We left it on there for 5 hours. Booyah, it activates. That means we were able to make it radioactive and then start measuring all the elements that are in there based upon the spin down half-lives of the elements that are present. So we do that. We get like an initial rough draft. Hey, we're seeing elements in here that is confirming what we already believe to be true about the elements present. And then we do the long test, put on a big old block of slightly less radioactive, but still very radioactive stuff. And we do it for a month. And nothing happened? What? It didn't become radioactive after sitting on a block of this stuff for a month? That's not supposed to happen. So then we put it back on the original thing. We leave it on there for a week this time instead of a couple hours. But it only got as radioactive as it did the first time after a week. That's all I'm gonna say about it for now. I want to not steal any of Dr. Sadagas' thunder, because he's got a pretty good thing to tell you here about what's going to go on. But so the summary, this is what I got for the latest Arts Parts update. The microsphere, the lead zinc microspheres, they happen to be arranged oftentimes in circular patterns that may relate to low frequency terahertz. Programmable quantum matter is something worth looking into for a number of reasons. Quantum dots especially are interesting for their relationship to terahertz output, and they can do a lot of other fancy things too. This quartz-clad gold nanowire happens to follow a lot of similar things about it to other gold nanowires used in terahertz functions. The not solid crystal, but instead the very small nanosphere-sized bismuth nanoparticles. It turns out that those actually may have some really decent plasmonic applications. There might be this whole area of plasmonics that we need to deep dive. And because it's bismuth, it can do some really fancy physics. There's a couple of different asymmetries that exist regarding bismuth that are worth pursuing further. And we have a terahertz laser ourselves. It's only a matter of time. Arrow released a short report that said it was slag. According to Hal Puthoff in a recent interview that I linked at the very beginning of this whole thing, there's a lot more than just slag in the much longer report. I got a bunch of extra resources there. There's papers galore within this stuff that if anyone wants to learn more about any of the things I've discussed. I had to read a lot of them. So I just want to end this with a super, super big thank you to the scientists that let me be a part and let me put together this new chapter of arts parts testing development. Like, I cannot express how grateful I am and how stoked I am at what should be coming down the pike regarding 3 samples instead of just our 1. That's what I got.